I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life. And guys, we have some bad news.
What bad news do we have?
Well, Melissa's not excited about today's episode, unfortunately. Normally she is, but we thought we'd start right out of the gate and make sure to tell you guys, rip the Band-Aid off cleanly, that Melissa's just not excited about this episode, and we're very sorry.
That is not true. Jam is lying to y'all. Okay.
Melissa couldn't contain her excitement and was talking about it before we even pressed record, and I was like, I have to...
I have to get out in front of this.
Yeah.
I even posted an Instagram and Twitter post about how excited I was.
Yeah.
I was excited from the moment I got this question.
Nice. Interesting. When did you get this question?
I got it recently. I went to the American Chemical Society conference in San Diego.
Mm-hmm.
And this question was emailed to me. And I opened it in the room of chemists, read it silently, and then read it out loud. And everyone also got excited.
Interesting.
Yes, it was the people in my lab group. I opened the email and I said, oh my gosh, someone just emailed us this question. And they were like, oh yeah, that's a good one. So
Nice.
I guess the listeners already know, but Jam does not.
Right.
So the question is from Micah Vale, and he said, my question is, why do lobsters turn red when you cook them?
I see. And what color are lobsters before that? They're like a brownish or something?
They're like brownish, bluish, blackish, like not red. There's sometimes a little pink around the edges.
Right. I remember hearing that they're blue at one point, but then like I've seen lobsters in the little tank and they're not, they're not blue. They're like just kind of definitely not red at all.
I got so excited about this question, I think partially because I had never wondered it. And that is the type of thing I should be curious about.
Right.
Like that's the type of thing I would normally think, why does this happen? And it never occurred to me to think that.
Yeah.
Which is part of what I love about this podcast is when listeners ask questions that I think, oh yeah, why does that happen?
Right.
And I knew immediately it had to be a sciencey reason. It had to be a chemistry reason. So I got really excited. I also used to work at Red Lobster. So I spent hours looking at lobsters every day of my life, and I never wondered it.
Yeah.
And I should have.
That's a very interesting extra tidbit there. You've experienced more interactions with lobsters than the average person by far.
Yeah, I worked there for 3 years, and I never wondered. Kind of out of character for me. Maybe I was just so worried about giving excellent service.
Right. And maybe also if you think about it too much, you think about how these things are like living and then they're dying. I mean, were they alive?
I did think
hanging
about
out?
that a lot. Yeah, you would have to I wouldn't do it. I never once, but you'd have to get the live one out of the tank and take it to the back. And I didn't want to experience that. So I would beg my coworkers to do it.
Yeah, maybe that's why you didn't think about it, because you tried not to,
Oh, yeah, that's a good point. So the answer to this is actually pretty straightforward, or it seems like it's pretty straightforward, but actually it's a beautiful backstory, which is what got me so excited about it.
Okay.
So lobsters' diets contain a pigment known as astaxanthin.
Okay.
Astaxanthin is red. It also gives salmon its pink color.
Oh, okay.
So they eat astaxanthin. I think it's present in plants and other things that they eat.
Mm-hmm.
And it's in their diet somehow. And it's an antioxidant. So it's good for them to eat. And that pigment will make its way from the lobster's skin into the lobster's shell.
Okay.
I don't know how it gets there. That's a biologist question. I just know that happens. Some magical bodily process that a biologist would know that I wouldn't.
Mm-hmm.
And when the pigment is in the shell, it is actually bound to a protein. And I think the protein is actually called alpha crustacyanin, so like crustacean cyanin, crustacyanin. And the red color, once it gets bound up by that protein, shifts to blue or black. So the pigment by itself, when it's free, floating around, is red. But when it gets bound up in that protein, it shifts color.
Okay.
When we cook the lobster, we've talked about this in the eggs episode. You gave one of the best analogies that you've ever given. The protein actually unfolds. That's what's known as denaturing.
Oh, right.
So when the protein begins to get denatured, when you're cooking this lobster, it actually releases the pigment.
Okay.
And when the pigment's not bound anymore, it's red again. So we drop our lobster into water, and the protein gets denatured, the pigment is unaffected, and so the primary thing we see as the protein breaks down is the pigment staying and making that bright red color.
Right.
And that's it.
Huh.
Sort of.
Oh, okay.
So that's a good thing you can tell your friends at parties. Oh, did you know that the reason that lobsters turn red is because this pigment is bound by a protein? I was like, oh, that's interesting. And then I got into the heart of today's lesson.
Okay.
Which is, why isn't the lobster red before? Like, why does binding that protein change the color of the pigment?
Right.
And up until the early 2000s, chemists actually didn't have an answer as to why that happened.
Dang, it's one of those like recent-ish things that like when we were little didn't know.
And actually, they might still not really know.
Oh, dang.
I know. One of the papers came out in 2005, and I was 14 then. I was taking chemistry. So as long as I've been a chemist, this has been a question that's happening.
Yeah. Dang. Interesting.
Okay, so let's talk about why this might happen when the pigment is bound.
Okay.
So just a review, we've talked about color a lot. But for things to be visible to us, their electrons have to be able to absorb energy and be excited into an energy level within the visible region. And different features about the molecule itself will dictate how those electrons can absorb energy. And that is what determines what color we see. So pigments, organic pigments especially, have alternating double bonds that have that ability to absorb light in the visible region.
Right.
Usually it's about 8 is when it starts to become visible to us, usually in the red region. And the more alternating bonds will sort of shift down the rainbow.
Okay.
When things are really dark, like greens, blues, blacks, those colors, they actually usually need an additional feature like a metal bound into it. So even chlorophyll has magnesium usually bound into it. Chlorophyll that's green, that makes trees green and plants green. So other features, metals being bound, and even the shape of the molecule, like how it's being held in space, that's also known as the conformation, can change this energy absorbance and the way that the electrons can move, and therefore it can alter the color.
Okay.
And this is also a lot of what I did in my research. If you want to go back and listen to the episode where I explained what my master's research was on, I was learning about photosynthesis and how we could make molecules that could absorb more of the region of light. So I would tweak molecules and change them to try to make them absorb more light. A lot of times we would have to make crystals out of the molecules that we grew and look at their 3D arrangement in space. And if you changed the way they were arranged in space, like how close they were to another molecule, it could impact how electrons were transferred in the molecule and impact how long the electrons could be excited, and also sometimes the color we saw.
Mm-hmm.
So that's a little bit of background on color, a very quick primer. You will learn more about color if you go back to some of our previous episodes about color. We recently re-released a few of them that I think would be really relevant. Okay, back to lobsters.
Okay, sweet.
So that was our primer on color. In 2002, some chemists tested a wide-ranging theory that when the pigment, that astaxanthin, was bound into this protein, that the conformation changed. So literally the pigment twisted and the conformation changed, and it was held there by the protein when it was bound into the protein.
Okay.
And there's a theory that that was what caused the shift in color. So that is what caused the electrons to change the way they absorbed and to move to this dark bluish black, where the protein, when it was bound to the astaxanthin, would bind.
Okay.
So they tested that theory, and they did find when it bound, it would shift and the conformation did change. So in 2002, a paper was published that stated the reason for the color change in lobsters when the pigment was bound into the protein was due to this conformational change. And that was the best information chemists had at the time.
Okay. So
But
just the way it's held, the shape it has a little bit was their
Yes.
main reason, main thinking there.
Yes. And when I first heard that, I thought, that's surprising to me that it would shift that much, because when I'm thinking as a chemist, red is like on the far left side of the visible region and bluish black is on the far right side, right? Like these are on opposite sides of the spectrum.
Yeah, yeah.
And so it's hard for me to imagine that just twisting the molecule would make such a difference that it would shift all the way across the visible region.
Yeah, right.
It doesn't seem like it would make that much of a change. So my thinking was maybe the protein was absorbing the light somehow, but I don't know a lot about proteins really, or how how they would absorb light. That's really a biochemist field more. So I thought, is it binding in and making a really large conjugated system that would make it highly colored? I'm kind of confused about that.
Yeah.
And I guess some other chemists were thinking the same thing, because, I've said before, when as a chemist or a scientist, you have the best information that you can gain access to, and that's what you function under. But you should always update your understanding, and you should always dive deeper whenever you can. And when new information that's based in facts come out, then we're going to update our understanding of this.
Right.
So computational chemists, I guess, were curious about the same things I was curious about. And they did a calculation. And computational chemists are incredible. They're very smart. They're like programmer meets chemist meets I don't know what, really smart person. And they can get computers to predict outcomes of reactions. And these are very, very highly powered supercomputers that have high computing power.
Okay.
So some computational chemists tried to predict how much the color would change based on this conformation shift and the binding. And computational calculations revealed that the twisting could really only be responsible for about a third of the color shift.
Okay, so on like about a third of the way across that spectrum?
Yes.
So it'd end up in like yellow or...
Yeah, yellow
something.
Or maybe light green.
Yeah.
So they theorized that when the proteins were bound up, a lot of times in the 3D arrangement, the pigments would cross each other sort of in an X formation. And they thought maybe that aggregation, the way that the proteins would come together, was responsible for the color change. That was the newest piece of information that they could come up with.
Okay.
And that aggregation, the way the molecules were arranged in space together, not just one individual molecule, but the way that two were crossing each other, that was the reason for the color change.
Okay.
And that was the best information we had at the time in 2005.
Okay.
But even more recently, in 2013, they actually found that the way those molecules were crossing together is a very weak association, and they attribute the color change to possibly an even more complicated molecular concept known as electron transfer.
Okay.
And that would be responsible for the rest of the color change, that other 2/3 of the way across.
Okay.
So really, scientists at this point in 2021 think that the reason that lobsters aren't red to begin with is because this astaxanthin is bound into a protein, the conformation changes, and something else about its environment and nearness to other molecules allows something at the molecular level to happen that makes this color shift from red all the way over to black.
Dang.
Blackish blue.
Dang.
Isn't
So-
that wild?
Yes. Man, you're right that it was simple and then it wasn't at all simple. And then it
Right.
got really complicated.
Got so complicated. But here's why I like this.
Uh-huh.
I think this story of lobsters captures so much about what it means to be a scientist.
Yeah.
Like each one of these people spent a lot of time. They did different characterizations, they did different calculations. They used the information and the knowledge that they had and the computing power that they had in the early 2000s to contribute a piece of information to the puzzle.
Mm-hmm.
And each time the technology developed, our understanding developed, we used it to apply to the situation and tried to learn new things. And each person only was zoomed in on a tiny piece of this, but when you put it all together, you have a deeper understanding of what's happening.
Yeah.
And I also love it because a lot of times things are presented in science class like we have this figured out. So it would be so easy for me to say, oh, this is why this happens, is because the pigment binds and it turns black because the conformation changes. And just leave it at that. Like we understand it perfectly.
Yeah.
But we don't understand it perfectly. It seems like there's still some mystery going on about it.
Yeah.
And I think that mystery and the humility to be able to admit that we don't know things is something that scientists needs to grow. Scientists as a whole need to grow in. And I think if we did more of that, there would be more space in our developing classrooms for young children and, who are in their science classrooms to spend more time wondering. Because I talked about this in the episode where I talked about my master's research, but whenever I got to my master's research and we talked about how we were trying to do artificial photosynthesis, I asked the question, why can't we just do it exactly the way the plants do? And the answer was that we didn't know how the plants did it.
Right. Yeah, it's like if we really did know every part of that, then we could. But it's like, we don't. Dang.
Right.
Yeah, that's crazy.
And but it gets presented like, here's photosynthesis, here's how it works, this happens, and we understand it.
Yeah.
But there's mystery, and in that mystery, that means there's room for us to learn more and to get young scientists excited about the way they can contribute to the field.
Yeah.
So I really, really love this story because it's both interesting and relevant to everyday life. And it reminds us that as scientists, we need to be humble and we need to admit what we don't know and that there's so much more going on that's hard for us to understand, even though we have done so much.
Yes.
And I think that's beautiful.
Yeah. Dang, well said.
Yeah, so this really got me very excited, as I mentioned. Maybe more excited than I've been before because it felt to me like it had every element that I love in a chemistry story. I was like, this is such a good one.
All the parts of a good mystery.
Yes, everything that you love in a good mystery. So then I was going to ask you to try and tell it back to me, and then I have some fun lobster facts.
Nice. Okay. For one, this is tough. a lot of the chemistry explanations are tough, and I end up, messing up language or words you taught me, or whatever. But what is hard is anytime there's like a lot of layers like this, I'm like, oh man, first time hearing it. And some of you guys who listen to the podcast, you probably have heard us explain that before, but like I literally am learning it along with you. And so, my apologies if anytime that it's like complicated like this, if my explanation doesn't really help you very much because I'm struggling, then I'm very sorry. It's meant to be helpful to you, but, my guess would be it's not always as helpful as hearing it from the chemist herself. But
well, that's part of why we do the 1-2 punch.
Yeah.
And that's the listener's opportunity to send us in a really good of their own analogy. Remember we had the person who said about the Greek god that had the baby and then switched back?
Yeah.
That was a really good one. So, and she was really nice, and her husband emailed us after and said, my wife was so excited. And I was like, that's so cute. I love
awesome.
that. So if you think Jams is more confusing, you can one-up him and prove that you would be a better co-host by sending us all of your ideas.
And then it'll be your problem. Now you're the co-host. I'm just kidding. So the first thing I thought of in terms of just an analogy is I thought of something that to me is complicated, to lots of people is complicated, and many stories of involving this end up being more complicated than we expect, is cars. So, what happens with most of us, rather than like a color change, like seeing something change, like the lobster changing color so drastically when we cook it,
right,
is you're hearing a noise of some kind. Something is happening that's different. I'm hearing a noise my car didn't normally make. And how often it is that as you start, either you yourself are exploring this, which I would never try myself because I would not fix it, but
I would make it worse.
Yeah, you take it to a mechanic or whatever. They start looking, and it might seem at first like it's one thing. And then they might mess with that a little bit. And it's like, well, you know what? This thing over here is also not doing the right thing. And you know what? This thing over here is also not doing the right thing. And before you know it, you're replacing a lot of stuff. But all those things together contributed to whatever caused the very obvious change to me, which was just the sound.
Yes, that's a good one.
A new sound that I didn't hear before, but and in the case of lobster, it's so obvious that color changes.
Yes.
But all things that are happening under the surface are a lot more complicated and interesting and crazy. But there's one very simple change we notice as regular folk that do not have laser vision or molecular vision. We just
molecular vision, my dream.
Yeah. We just see, hey, isn't that thing red now? And then when we try to explain it, or hey, why is my car making a clinking sound? Or why is it humming a little louder than normal? Then we are forced to be faced with our lack of understanding.
Yes.
And it's not a simple answer in so many situations.
Yes.
Which is sad news for our wallets when it happens to our cars. But interesting news for our brains when it's with lobsters.
Well, also, I think you can think of it too as like the sound starts happening. So your car's running fine. The sound starts happening because all the things went wrong. The mechanic fixes them, and then it goes back to running fine. So the pigment starts out as red.
Right.
And then it turns blackish blue, and you're like, oh, this isn't good.
Yeah.
And then we free the pigment, and it's red again, which for the pigment, probably good. For the lobster, might not be as good. That's not where I thought you were going. I thought you were just going to say we turn the car on, and it goes, and then we turn it off, and it stops. And it's as simple as turning the key, but in reality, it's complicated because this machine's doing all this stuff for you.
Right. Yeah, that also makes sense. I mean, I guess the main part's still true about the cars being complicated. But yeah, I was thinking about when a change happens that we're like having to investigate, Yes,
yeah.
But so back to the lobster, to try to do my best to explain the actual pieces of it, is that there's a pigment and it's part of its diet. Did you say it's from a plant? lobsters eat?
I think it's from a plant.
Yeah.
Yeah, I'm pretty sure.
They don't just eat pigments on their own.
Well, who knows?
Lobsters love pigments, boy.
I can honestly say I don't know anything about the day-to-day life of a lobster.
Yeah. And that's how they prefer it. They like to live this aloof, chill life until we pull them out of it. So
what if when we ate blueberries, our skin turned blue, like Veruca salts?
oh yeah.
Was it Veruca who turned blue?
I think it was. Yeah. I think it was
Like
her.
that's what happens to them. They eat plants and their shells turn red.
Yeah. I mean, there is that can happen with us with like, what is it, like carrots and tomatoes or something like that? Or some
Yes.
vegetables, if you eat just
Yeah.
an insane amount of them, that it turns you orange.
That's true. Yeah.
But so okay, yeah. So they eat a lot of this stuff that has this pigment in it, and the pigment it's in their skin and then goes into their shells and is there. But as it finds its way into their shells and stuff, it becomes, what did you say with the proteins? It becomes bond.
Yeah, with proteins, they usually have, I think it's through intermolecular forces, but they usually have a shape that's just right for the molecule to fit into and all of the bonds that it needs. So I think it's or all of the molecules it needs to do intermolecular forces. I think it's a lot of times hydrogen bonding. I don't know for sure, but when I usually say binds to the protein. Yeah.
I knew I needed to get that word correct and that I didn't hold on to it. So binds.
Yes.
Intermolecular forces are at play just like they always are. And
yeah, most likely. I mean, that's what I think it is.
these proteins that are in the shell of the lobster, they sort of bind around these pigment molecules. And so that is kind of where the action is happening. The more interesting, mysterious part, because we know that once the proteins denature when we cook it, that undoes that and it becomes red. But what's happening here that makes that pigment be blackish bluish?
Yes.
And that's where all those other rabbit holes happen, correct?
Right.
Okay. So one of the things you said was that when it binds, you said the word composition?
Oh, conformation.
Conformation.
So like, it's conformation, not like conformation that you do in Sunday school or whatever.
Right.
But
conformation, the shape?
the formation of it. So
formation.
the way it's arranged in space, the 3D arrangement of the molecule, because you can rotate around single bonds. Single bonds can twist around really easily. That's known as the conformation.
So
the actual shape of it.
Got it. So the hypothesis there for a while, the guess was the changing of how it's conformed, how it's formed, the shape of these molecules must be being changed a little as it's being held by the protein.
Yes.
Bind by the protein. And that is changing the color.
Right.
Because it's affecting how the electrons take in energy and the energy levels, the way they put off light that we can see. But it seems that couldn't be the only explanation.
It was calculated that can't be the only explanation. It seems that conformational change, according to the computational chemists, only accounts for about 1/3 of the color change.
Right.
And the rest of it is sort of still a mystery.
The next thing that was brought up was that the other, oh man.
This part is kind of confusing, so I don't think you have to explain it.
Okay.
I think this part is still up in the air. So initially, the idea was the proteins are close. It's like two proteins bind two of these molecules are close together and they form an X, was my understanding based on the paper. The pigments form an X. And they thought that association between the molecules made it so that the color was changing. But then some other scientists did some research and felt that experimentally, the association between these two molecules was pretty weak, and it actually didn't account for the rest of that. And they think it might be something else, some type of electron transfer. So, yeah.
Yeah. Okay. So there's the other things you said, the other hypotheses, explanations, and stuff, but that are still up in the air.
Mm-hmm.
But either way, we know that then when we do cook these lobsters, it denatures the proteins, which lets the pigment go free, be itself as it was before. And so then it's back to being red.
That's right.
And did I miss something in there?
I don't think so.
Okay.
And
other than the part that was super hard.
Yeah, but I want to say also, if I miss something, if you know of a more recent article than this 2013 one, where they could confirm what else was making the change, please reach out and let us know. I could not find a more recent article on this topic, but if you're a lobster scientist, if you're more up to date on the ins and outs of this protein and this pigment and why they interact, we want to hear from you.
And this is probably unlikely, but if you yourself are a lobster and you'd be kind enough to explain it to us without the use of science and just kind of tell us what's going on there, then that I think would be fine too. I'd be okay with that. So
that would be amazing.
Yeah.
Okay, so
for some reason when you said if you're a lobster scientist, I just in that moment imagined what if you just stopped right there? If you're a lobster, so that's why.
Also, what if I just said if you're a lobster scientist? Like, what if you're a lobster who's also a scientist?
Yeah.
That really makes me want to get like a little lobster in a lab coat with goggles on. So cute. If you're a cartoonist, we want to see that. That would be adorable.
Yes, but you got to make sure the lobster in that cartoon is not red because we want it to be alive.
Yes, we want it to be alive and we want it to be cute.
Yes.
I really hope someone does that. Okay, I have no artistic skill, but I can dream up ideas. I just can't make my hand do it.
Yeah.
Okay, so you've earned some fun facts.
Okay, sweet.
The first person who did a good job of explaining this that I found on the internet was actually someone who studies shell disease in lobsters. And I guess it's easier to identify if the lobsters are a specific color. And so he manipulates the color of the lobsters to be able to study the shell disease. So he showed us a lobster that lacks the ability to produce proteins that can twist the pigments.
Oh.
And those lobsters are only red, even when they're alive.
Huh. Weird.
Because they just don't have the protein. Yeah, he showed us the lobster and he said, this lobster's mom also is this color because genetically they can't make the proteins. And I was like, those proteins seem like they could be important because I feel like the not having the red color means that they can blend in. But if you're bright red,
right.
I don't know. Maybe that far down in the ocean, though, light sort of changes. So I don't know.
Yeah, maybe it's not quite as like being like with other animals where it'd be like, oh, you can be spotted by a predator way easily.
Right.
Maybe that's not quite as much of a concern for lobsters. I don't know.
Right. Or maybe it is a concern and that species dies off rapidly and that's why we don't see that very often.
Right. Yeah, it's not an advantageous mutation, maybe.
Right. And then he also said that if the lobsters don't eat that pigment, they are just only blue. So they don't have any red coloring at all to them. Normally lobsters have like a little bit around the edges, you can tell.
Yeah.
And he held up a straight blue lobster and it was kind of cute. So he doesn't feed them the pigment so he can more easily study the disease. But he also has that one pink one.
Got it. Weird, dude. That's interesting.
Yeah. He held them up on camera and they were actually pretty cute. So if you want to go click the links in our references and check them out, we encourage you to do that.
Nice.
So the color really depends both on their diet and their ability to make the protein.
Yeah.
Okay, so that's everything I have for you today. But I also wanted to say my happy thing first.
Okay.
So I said already, I got this email when I was at the American Chemical Society conference in San Diego.
Mm-hmm.
And that was so fun.
Nice.
That was my exciting thing this week. I got to meet other people in my field who are so kind and encouraging. And I was able to share my research with peers in my field, which I haven't been able to do ever in this field. So that was really exciting. And I wanted to tell our listeners that this summer I will be at BCCE giving a talk about chemistry for your life. So if you're a chemistry educator, if you're going to also be at the BCCE conference this summer, please reach out. I'd love to do a chemistry for your life meetup at BCCE because I was sad that I didn't take the opportunity to meet with chemists that listen to the podcast at the American Chemical Society meeting.
Oh, yeah.
So that's why I wanted to go first. If anyone dips out at the end, I wanted to really talk about that real quick before we get into personal life stuff.
Nice.
So that's something that happened to me this week. But I want to know about your life, Jan, because I've been out of town, so I have no idea what's going on with you.
Yeah, that is a great point. Okay, so mine is not that cool to most people, but you and I, like you said, we haven't talked in a little while. We don't get to hang out.
True.
You were out of town. You were ignoring me and trying to hide
I wasn't.
and stuff like that. I'm just kidding. But
I mean, I wasn't ignoring you any more than I'm ignoring everyone else.
I'm just kidding.
Honestly.
So because of this podcast, it actually forces Melissa to have to hang out with me. So it's pretty great.
It's true. I've seen you more. You're the only person that I've quote unquote hung out with, if that's even what you can call this.
Yeah.
Since I think mid-March.
Yeah. There we go. So it's working out pretty well in my favor. So I often update you and the listeners here about any happenings with my cast iron life.
Oh, yeah.
So what happened recently is I have been, if you're new to this and you're like, this is the first time I'm hearing some sort of cast iron update, listen to our cast iron episodes, which are probably about a year ago or a year and a half or something like that.
And recently you shared you made your first steak.
Oh, that's true. I did share about that recently. Yeah, that's true. So this was a sort of sad one where I started having a lot of flaking on my smaller cast iron pan, which is the one I use most often. It's about an 8-inch or 9 or 10-inch one. And
flakes of polymer
coming off pretty consistently. At first, I was just trying to heal those sections by doing some more reseasoning and stuff, which some people say just do that. Don't reset it, because if it's just a little bit of flaking, it might just be some sort of imperfection in a few layers down, and it'll all be okay in the end.
You can cover it up if you make a solid polymer above it.
Yes.
Yeah.
But what I was noticing is that I kept having chipping in other areas too.
It was a uniform problem.
Kept happening over and over. I couldn't heal one area faster than another one would chip. And
man,
I know.
I wonder what happened, if you heated it up too hot or.
Well, here's my theory. This is not science. This is what we call stuff I found on the internet. And basically, flaxseed oil is one of the oils that tons of people have been recommending people to use for a while.
Yeah.
But one of the problems people have found after they used it for a long time is that once you get a lot of layers of seasoning, it's really, really hard. These layers of seasoning, the layers of polymer are really, really hard.
Yeah.
But apparently when you get a lot of them, it starts to get brittle, and then a lot of it can come off, which I don't know if those are the right words, but it is very strong. But somehow when you have a lot of it, it will just break off in chunks, like whole pieces can come off.
Interesting. I feel like that would be something that a surface or materials chemist would be able to shed more light on, or maybe a polymer chemist.
Yeah. So I had to start over on that pan. And
did you use flaxseed, or did you decide to go back to good old
So I moved on to where the current cast iron internet community is going, which is grape seed oil.
Grapeseed, that's
Yeah.
what it was. Yeah.
And
Wow.
I did a few layers of seasoning, and guess what? This is like just slightly on topic. Instead of looking deep jet black like flaxseed oil does after you've done a lot of seasoning layers on it,
It's bright red like lobsters.
it's bright red. Yeah. It looks a little bit brown.
Oh, yeah. Interesting.
It looks especially brown next to my very black pan that I did not have to redo. That has flaxseed oil only. So,
What's the non-stickiness like?
so far solid? Just
Nice.
just as good as old flaxseed, in my opinion. So
We probably need to do a reseason. I don't know that we need to really sand it down or anything, but I think we probably just need one solid coat on top of everything because
yeah,
our non-stickness has been it leaves something to be desired.
what I was telling your husband about is that I don't ever sand anything. I just do the self clean oven
Yeah.
setting, and it makes the starting over thing so easy without having to like get in the
Work.
yeah,
Yeah.
sand things off and put particles of polymer all into the air and breathe
Well,
it in
our
and
oven
stuff.
doesn't have a light or a window, so I very much doubt that it has a self-cleaning option.
Yeah, yeah.
So,
Does it have a window? Really?
no.
Interesting.
Has a solid metal door. You don't know how I, as a baker, struggle with that.
Yeah, I've never experienced that before. I don't think.
Yeah. I mean, we live in an apartment, so it's probably just the cheapest model that they could get
Right.
in bulk. But
Right.
this is not the oven that I will have in my forever home. I'll tell you that.
Right. So, all you listeners, thanks for listening to that really boring explanation that five of you
I liked it.
liked it, and Melissa. But that's just the latest sort of chapter in my cast iron life.
And write in. We want to hear about your cast irons.
Yeah, definitely. We know some of you guys had to have been as affected and convinced by the science of cast iron as Melissa and I were.
Yeah.
So tell us what you've been up to.
Yeah, please do. Well, thanks. I didn't know that grapeseed oil was a thing. I think I was thinking of something came before flaxseed oil, but I don't know what.
Yeah.
But maybe canola is what I was thinking. But I'm so happy. I'm glad that you updated me on the information. I'll look for grapeseed oil.
Yes. Yes.
So thanks for your cast iron updates, Jam. And thanks to all of you listeners for coming and learning about lobsters. And this really made me so happy. So thanks for bringing me joy in the middle of my dissertation demise.
Well, thanks for teaching us. And listeners, thank you guys for the questions you write in. And if you have a question or an idea or a thought about something that could be chemistry in everyday life, please reach out to us on Gmail, Twitter, Instagram, or Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the cost of making it, go to ko-fi.com/Chem for Your Life or click the link in our show notes to donate the cost of a cup of coffee. If you're not able to donate, you can still help us by subscribing on your favorite podcast app or rating and writing a review on Apple Podcasts. That also helps us to share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. References for this episode could be found in our show notes or on our website. Jam Robinson is our producer, and we'd like to give a special thanks to V. Garza and S. Navarro, who reviewed this episode.